Hi guys. Today we're looking at Unit 3, Linear Functions, and specifically 3.4, Word Problems. Today we're just looking at systems of linear equations. So before we move on, we want to recall what is a system of equations. We know that's two or more linear equations, and these are including the equal sign, so these are not inequalities. So three types of systems of equations. The first, we have one solution. So when we have one solution to a system of equations, we're looking for that point of intersection, right? So where are both of those equal? And then the second type is no solution. So if we graph those linear equations, we see something like this, where we have parallel lines. There is no point of intersection, so there is no solution. And lastly, we could have infinite solutions, meaning that those equations are just the same line. Okay, so these are three types of solutions for systems of equations. So when we are solving these, we can of course graph, like we saw previously. We can also use elimination or substitution to find the solution to a system. Okay, so first example, you sell tickets for admission to your school play and collect a total of $104. Admission prices are $6 for adults and $4 for children. You sold 21 tickets. How many adult tickets and how many children tickets did you sell? Okay, so first thing I want to do is I kind of want to just mark up my word problem and annotate. So I see that I have a total of 104 altogether. And I'm selling two types of tickets. I have adult tickets, which are $6, and children tickets for $4. I know that all together I sold 21 tickets. Okay. And I'm trying to figure out how many adult tickets and how many children tickets I sold in total. So when I'm looking at a word problem, I want to first define the variables. What are the unknowns in the problem? So I do not know how many adult tickets and how many children tickets I have. So I'm going to define those as my variables. And I don't have to use X and Y. I'm just going to use A and C for this example because it makes sense. So I'm going to define variable A as number of adult tickets and C, number of child tickets. Okay, so now that I define my variables, I want to go ahead and start thinking about a system. In this case, two different equations that I can write from the information given. So when I'm looking at the problem, I know two types of information. The first information I know is the total number of dollars, okay, the total amount that they've collected. The second thing I know is the number of tickets altogether that I sold, and that's 21. So one equation is going to deal with the money, the number, the total that I've collected. So I know that each adult ticket is worth $6, so I can represent that total amount as 6 times A. That will give me the total that I collected for my adult tickets. And then if I add to that the total collected of children tickets, I know I have $4 for children tickets. That can be represented as 4 times C. In total, I collected $104. So I can represent that with this equation. That's my first one. Okay. The other information I have is that I have a total of 21 tickets, meaning altogether adult and children tickets, total 21. So I can represent that as A plus C, the number of adults, plus the number of children tickets is 21. So I have written a system from the information given. I have two variables. I want to go ahead and solve. So remember, there are three ways to solve any system: graphing, elimination, or substitution. You can employ any of those methods. If you graph, we need to make sure that we are putting those in y equals form, slope-intercept form, and using our graphing calculator. So I'm actually just looking at my equations here. I think elimination would be the best method for me. So I'm going to go ahead and use elimination. I'm going to just rewrite these as 6a plus 4c equals 104. A plus c equals 21. Okay. And I want to multiply by a number that is going to help me cancel out one of my variables. So I'll first focus on canceling out my a's. So that means I'm going to multiply everything by -6. Okay. When I do that, I'm going to get my a's canceling. I'm going to get a -6c. 21 times -6 is going to give me -126. And I'm just adding down. So 4 minus 6c gives me -2. 104 minus 126 gives me -22. And solving for c, dividing both sides by -2, I get c equals 11. So again, C is the number of child tickets, so I already found C. But I can't stop there. The second step is I want to find the number of adult tickets. Now, to find the number of adult tickets, I can plug in C. It doesn't matter into either one. I can plug into A plus C equals 21, or the first one. That one's easier, so I'm just going to plug that in. A plus 11 equals 21. I subtract 11 from both sides. Okay, A is equal to 10. Okay, so I found the number of child tickets, the number of adult tickets, but I can't leave my answer as just these variables because these are things that I define. So when I have a word problem, I always want to interpret my solution and answer the question. So the question asks, how many adult tickets and child tickets did I sell? So I sold 11 child tickets and 10 adult tickets. Okay, I'm done with that one. Okay, moving on. Next, I want you to pause your video and try the You Try problem. So go through this one exactly like we did the previous. And I'll come back with just the solution for you. Okay, so hopefully you pause that video. Here is the solution for this You Try, 5 $10 bills and 9 $20 bills. So we're going to move on now to example 2. Example 2 is a different type of setup, and I just wanted to show you this type of problem. So example 2 says a landscaping company placed 2 orders in a nursery. The first order was for 13 flower pots and 4 trees, and total $34. So I'm going to have 2 variables here. I have the number of flower pots and I have the number of trees. The second order was for 6 flower pots and 2 trees, and total $16. Circle the totals. The bills do not list the price per item. So what we do not know is the price for flower pots and the price for trees. So those are going to be our variables. So in this one, I'm going to define X as the price of the flower pots. Price. Flower pots. And Y as the price of trees. Okay. From there, I want to go ahead and set up my system. So in the previous example, one problem dealt with the price or the total overall cost, okay, or dollars, and the other one dealt with just the total number of tickets together. In this one, I'm given the total number of pots and trees for each one, but I have 2 different orders. So each of these equations is going to deal with the total price. So I have 13 flower pots, 13X, and that quantity would give me the total I spent for my flower pot, plus 4Y equals 34. That's for my first order. Okay. The second one would be 6X plus 2Y equals 16. And I'm going to go ahead and solve this. Again, I'm going to use elimination. So using elimination, I'm going to multiply by a number that I can eliminate one of my variables. And it looks like it's going to be easiest for me to eliminate my y's first if I multiply by -2. So I'm going to go ahead and do that and rewrite both of those equations over here. So I get 13x plus 4y equals 34. And multiplying by -2 gives me -12x minus 4y equals -32. And we go ahead and cancel out our y's. I'm left with 13x minus 12, which gives me 1x equals 34 minus 32, gives me 2. So we find that x equals 2. Going ahead and plugging that in. It's my first step. Second step, 6 times 2 plus 2y equals 16. 6 times 2 gives me 12 plus 2y equals 16. Minus 12 on both sides. 2y equals 4. I'm left with y equals 2. So remember, I'm not done there. I have to interpret my solution. So the price of flower pots is X. So I have $2 for flower pots. $2 for flower pots. And $2 for trees. Okay. Great. So again, in the next one that you try, I'm going to pause, or you should pause your screen and go ahead and give this one a try. Okay, here's a solution for the U-Try. Be careful with this one. In this one, we are setting right these two equations and finding where they are equal. So we find after 10 months, Mr. Grazzi will save more than